Okay, so yesterday we talked about acceleration, and today we're going to talk about acceleration near Earth's surface. And what I mean by that is acceleration due to gravity. So there's lots of different rides and things like that which take acceleration due to gravity. Like you can consider a roller coaster as also being a gravity ride. You lift it up, and then you let it go. But my question is, does the mass of an object affect its acceleration near Earth's surface? So take a look at drop zone. In this case, do the number of passengers affect how quickly it accelerates down when it's released? It's a tricky question to think of. And put another way, if I were to take, say, my pencil and my calculator, the calculator is a lot heavier, and I were to drop them at the same time, which would get to the ground first? Calculator, the pencil, or would they both arrive at the same time? It's easy to test. You just go 3, 2, 1, right? And you can actually probably watch that in playback in slow motion because I'm recording it. But the interesting thing is, and let me skip ahead. Galileo actually, the myth, I don't know whether he actually did it or not, but the myth is that he went to the top of the Leaning Tower of Pisa and he would throw off different objects of different masses and compare when they hit the ground. And what he determined was actually fascinating. He determined that all objects, regardless of their mass, accelerate downwards at the same rate. Now this is sort of a little bit against common sense, because I'm sure if you were to drop an apple and a feather, it's easy to say the apple's definitely going to make it to the ground first. And you'd be right in that case, but the reason you'd be right is because air resistance is slowing down the feather. On one of the Apollo missions, it wasn't the first one, I can't remember which one it was, but on one of the Apollo missions, an astronaut took a falcon feather and a hammer on the moon where there's no air and dropped them, and they both fell at the same rate and hit at the same time. Now, of course, the rate of acceleration on the moon is a lot smaller than the rate of acceleration on Earth because gravity is different. But it doesn't change the fact that they accelerate at the same rate and they will fall at the same rate. Now, on Earth, that rate is 9.8 meters per second squared. On the moon, it's 1.6, but we're not going to focus too much about that. Okay, so we say an object is in free fall if the only force acting on it is the force of gravity. Okay? And the force of gravity causes an acceleration of any object, regardless of mass, to fall downwards with an acceleration or a rate of 9.8 meters per second squared. Okay? And we'll sometimes write that as g instead of a. Okay, because we're being very specific about what the acceleration actually is. Okay. Now it's also important to note that 9.8 meters per second squared is not a constant. Right? It changes. Right? If you were to go up to the top of Mount Everest, it would be slightly smaller than that. Okay, the closer you get to the center of the Earth, the larger it is. Okay, so an interesting example is the value of g in Mexico City is slightly lower than 9.8. And when they had the 1968 Olympic Games, a lot of the high jumps, long jumps, and pole vaulting records were all broken that year. Was it due to gravity? Don't know. Can you just pause there? All right, so right now, if you're just sitting, right, Earth is pulling down at you at 9.8 meters per second squared. Right, it's also pulling down. It's like pulling down your blood as well. But your heart's strong enough that it can still fight against gravity and pump it to your brain. But of course, pilots, especially like pilots of like jets or like military jets, depending on what kind of maneuvers they're doing, they could actually be doing a maneuver that's causing an acceleration much, much greater than 9.8 meters per second squared. Right? When that happens, we call it g-force. Even though we call it g-force, it's not actually a force, it's an acceleration. Right? 2 g's, for example, would be 2 times 9.8. 3 g's would be 3 times 9.8. And if you have enough g-force, right, in that case, your body isn't strong enough, your heart isn't strong enough to get your blood up into your brain. When that happens, you black out. Right? And in 1941, Canadian pilot and also an inventor named W.R. Franks, he designed an anti-gravity suit. Now, an anti-gravity suit isn't what you would think of from like sci-fi movies where you can go like floating around. What an anti-gravity suit is, it prevents pilots from blacking out. Not 100%, but they can withstand more G's with this suit on. And what it does is it basically it almost like pushes on all your blood vessels to actually cause or prevent your blood vessels from expanding outwards, so that it helps to keep that blood pushed up to your brain. Okay, so moving on. Okay, a lot of other examples of when acceleration is important. Things like airbags. Right? The most dangerous thing is in a car collision is the acceleration. Right? You can go from 100 to 0 like that. And in that case, what you need to do, or what your car and the people who design your cars need to make sure, is that the occupant experiences a much lower acceleration. They need to bring you down from, say, 100 to 0 over a longer time interval. And to help do that, you have things like airbags, for example, right? To sort of slow down or reduce your acceleration, right? To help avoid injury. Okay, last thing I want to mention is terminal velocity. So, again, if you take something and you drop it, every second, its speed is going to increase by 9.8 meters per second. Now, in reality, on Earth, where we have an atmosphere, air resistance is fighting against that. So you're not going to increase your speed forever, right? If you were falling for an hour, which wouldn't happen, you'd hit the ground before that. But if you were, your speed would not increase forever at 9.8 meters per second every second. What happens is, as you fall, the faster you go, the more air resistance there is. Okay, I'm sure you can sort of visualize this, like if you're in your car and you're driving at, say, 40 kilometers per hour and you have your window open, there's a little bit of a breeze, right? But if you're going at 100 kilometers per hour, there's a much stronger breeze. Right? Same thing when you're falling. The faster you go, the stronger the breeze. And that stronger breeze actually reduces your acceleration. Go from 9.8, for example, to 6, to 5, and you're going faster and faster. And as you go faster and faster, the stronger the air resistance is. And so you go like 4, and 3, 2, 1, and eventually your acceleration won't exist anymore. It'll be 0. When that happens, we say you've reached terminal velocity. Okay? And terminal velocity is different for different objects. For example, for humans, the terminal velocity in the air is about 53 meters per second or 190 kilometers per hour. But again, that's still sort of an estimate. Like, you can change that based on whether or not you want to fly like this or fly like this. Like, increasing or decreasing the surface area that's in contact with the air will change that. Right? And you can create a lot of surface area by setting out your parachute, and that'll make your terminal velocity then a lot slower, because obviously 190 kilometers per hour is very, very fast. And so before you reach the ground, you're going to want that parachute. Alright, so before we try some problems, okay, so let's go over some practice problems. And the first one says a ball dropped from rest, so that already tells us that our initial velocity is 0 meters per second from the roof of a building. after 2.6 seconds, so after a time interval of 2.6 seconds, the ball has a velocity of 25.5 meters per second down. Okay, so that's our final velocity. 25.5 meters per second down. Determine the acceleration due to gravity on Earth. Okay, so this usually sometimes we'll do an experiment. You can even try this at home. You just take a ball, drop it, time how long it takes to fall. And finding the final velocity, though, we would need some equipment to be able to measure that final velocity. But in this case, we can calculate the acceleration and sort of confirm that it's 9.8. And if you remember our equation yesterday, it's V2, or V final, sometimes I write 2, and V initial, sometimes I write 2 and 1 instead of final and initial. Doesn't matter. Over your time interval. Okay, so V initial is actually 0, and V final, 25.5 meters per second down over our time interval of 2.6 seconds. You can try that in your calculator, and you will get 9.8 meters per second squared. Right, but again, if you were on the moon and you were to drop something, it would not be 9.8. Right, similarly, if you were at Mount Everest, it would be slightly lower than that. Just pause that. Okay, so the second question, question number 2, says a flower pot is knocked off a window ledge and hits the ground 2 seconds later. Okay, now in this case, I didn't actually say it starts from rest. You kind of have to infer that. Right? If it's knocked off a window ledge, it means it was sitting on the window ledge and would have been at rest on the window ledge. So we can say the initial velocity is 0 meters per second. And then it hits the ground 2 seconds later. So we have a time of 2 seconds. And if we ignore air resistance, which we're always going to do in this course, with what velocity does the flower pot hit the ground? So we're looking for final velocity. Now in our equation, if we look at our equation, A equals V final minus V initial over time. In this case, we know initial velocity and we know time. But in order to find final velocity, we need to know acceleration. It didn't actually say what the acceleration is in here. In these types of questions, you need to realize that, unless they say otherwise, we're on Earth. And if we're on Earth, we can assume A, right, to be 9.8 meters per second squared down, the acceleration due to gravity. And if you want, you can even write that as G, so that you remember. So now we're going to have to rearrange this equation. Well, initial velocity is 0, so we can just get rid of that. Multiply both sides by time, and we'll have time times gravity equals our final velocity. So our final velocity is then equal to 2 seconds times by 9.8 meters per second squared down. Which is 19.6. It's 19.6, but I can round to 2 significant digits and just simply say 20. Okay, I'll pause there. Now question 3, we have an astronaut on the moon. If we're on the moon, G is not 9.8. So if I specified that we're not on Earth, like in this question, you cannot assume that G is going to be 9.8. An astronaut drops a tool from rest, which actually happened, remember. From rest, meaning our initial velocity is 0. After 1.3 seconds, so we have a time of 1.3 seconds, the tool has a velocity of 2.1 meters down of velocity. Oh, that's a mistake. It should be 2.1 meters per second down. So final velocity is 2.1 meters per second down. Determine the acceleration due to gravity on the moon. So g for the moon, it's the same equation. Final velocity minus initial velocity over time. Our initial velocity is 0. So we're just left with final velocity, which is 2.1 meters per second down, divided by 1.3 seconds. And we get an acceleration due to gravity on the moon as 1.6 meters per second squared down. Okay, I'll just pause. All right, so our last question goes back to some of the math skills we did in the beginning of the course, where we're actually doing an experiment. And the reason why I have this question is usually we do an experiment during this lesson, but we're online, so we won't be doing that. We have 2 students perform a lab and determine an acceleration due to gravity of, so you do an experiment, just like the one I mentioned. You take a ball, you drop it, right? You can figure out the time it takes by using a stopwatch. Initial velocity, if you're just dropping it, is going to be 0. And then we have some equipment in the school that can measure the final velocity, okay? Almost like a radar gun. Okay. And then you can calculate what gravity actually is. And so let's say we have some students do this and they get a value of 8.7 meters per second squared down. Does that mean gravity is wrong? No. Does that mean the students are wrong? No. It just means there's experimental error. Anytime you perform an experiment, you do measurements, there's going to be error involved, especially when you do a lab where you're relying on like human reaction time. Right? There's definitely going to be lots of error. So that's actually a pretty good value. The question says, like, how good a value is it? What's the percent error? How far in a percentage is this value from the actual value? So you can go back to our first lesson. Here's the formula. Percent error is the absolute value of your experimental value minus the accepted value, all divided by the accepted value times 100%. So if we're doing this with these values, our experimental value was 8.7 meters per second squared, minus the accepted value, which is 9.8. That's going to give us a negative number, but remember, the absolute value signs, just say ignore the negative, just remove it, make it positive. Divided by the accepted 9.8 times 100%. When we do that, we get an error of 11%, which is not bad for this lab.